a belt and pulley problem. We have a pulley, it's got a 20 centimeter radius, driven by a belt that goes around another pulley that's got a 30 centimeter radius. We know the torque on the 20 centimeter pulley, that's the one that's driving it, and the question is, what's the torque on the 30 centimeter pulley? Let's draw a picture of this situation. Here is a pulley. This is my 20 centimeter pulley. Radius is 20 centimeters. And this one's a little bit larger. The radius here is 30 centimeters. And there's a belt that connects the two. So this belt runs around this pulley, and it's a continuous belt. And if this is moving here and this is moving here, well, I want to be able to figure out, the question is, what's the torque on this 30 centimeter pulley? I know what the torque is on the 20 centimeter pulley. That torque is 15 Newton meters. Well, here's what provides the torque. It's this belt. So if this is turning this way, then there's some tension here, force of tension, that's making this 20 centimeter pulley spin around. And that tension is also pulling on the other belt and making it spin around. So maybe the torque is provided by a motor or something here, but the torque on this pulley is provided by the belt. If this belt doesn't break, then that means the force of tension is the same everywhere. It's not rupturing, so that means that force is continuous every place. So here's what I could say. I could say that the torque on the 20 centimeter pulley, that's equal to that tension times its lever arm, which is 20 centimeters. But the 30 centimeter torque, that would be equal to the same tension, but times a radius of, or a lever arm of 30 centimeters. So if tension is the same, I'm going to solve both of these equations for tension and see if I can get rid of it, because that's really not what I want in this problem. So solving this equation for force tension, I get tension is equal to torque for the 20 centimeter pulley divided by 20 centimeters. And the tension over here is torque 30 divided by 30 centimeters. Setting these equal to each other, because remember the tension is the same all throughout that belt, we get this simple equation. Torque 20 over 20 centimeters is equal to torque 30 over 30 centimeters. Well, torque 20 was 15 Newton meters. We knew that one. So this is just a cross multiply and divide problem. And we find out that the 30 centimeter pulley's torque is equal to 22.5 Newton meters. So generalizing from that last problem, we could set up this equation that might be a useful one to put in your toolbox. The ratio of a torque to the radius of a pulley is equal to the ratio of a torque and radius of a different pulley that are connected by the same belt, or chain if it was a gear. And then because diameter is proportional to radius, we could also say this: torque 1, diameter 1 is equal to torque 2, diameter 2. Let's not confuse this with distance. That's diameter is what we're talking about here. And for gearing systems, we've already seen that number of teeth is proportional to radius, so here's another thing that could go in our toolbox. For gearing systems, the ratio of torque to number of teeth is constant throughout the gearing system.